Before I start to introduce this part, I want to first give a little bit background on our group's work. I graduated from UIUC in 2011. So during my PhD, my work is mainly on this so-called model level commendation. It's like mostly related to ensemble learning. So later after I graduate, and I was thinking what topic I should work on. I want to find a topic that is relevant to my PhD but different. At that time, my lab mate, Wu, actually was working on this truth discovery problem. I talked with him and found that this truth discovery problem is very interesting. And it's about this multi-source data integration. So basically, I can work on this information integration at the data level. So therefore, when I start my own group, I start to work with my students on this truth discovery topic. And then during this process, we found that crowdsourcing is actually a very important application for truth discovery. Because when each user is making his own claim, it's very likely that this user is giving some errors. So therefore, we want to integrate all these different users' responses to find out the truth. So that's when we enter this crowdsourcing field. So I will talk about this passive crowdsourcing scenario, and my PhD student will later cover this active crowdsourcing part. So she has done quite some work on this truth discovery method, but now her recent focus is on this active crowdsourcing scenario. So when we talk these two parts, some of this work is from our group. So there is two papers we are not covering today, but you can see at this PhD. So my student Hoping has two PhD papers on truth discovery. So one is about this truth discovery with some theoretical guarantee. And another paper is about deriving some confidence intervals for the truth estimation. So please drop by our posters on Tuesday. And I still want to mention that there are still quite some challenges in these two scenarios. So we will hopefully, there are still many open questions for people to explore, and we are also continuing working on this part. So I recently got an NSF Career Award supporting our research on this topic. So we will still work on some more solutions. So for this passive crowdsourcing scenario, so the difference from active crowdsourcing scenario is that here we suppose the data are all already collected, and we just want to extract truth from this data. And in active crowdsourcing scenario, we can actively solicit information from users. But when we work on this passive crowdsourcing scenario, we found that there are some challenges that previous truth discovery methods did not consider. So therefore, we propose methods to address these new challenges. So what challenges we will be covering today? So there are these four major challenges we will talk about. So the first is this source correlation. Previously, the truth discovery methods, they assume sources are independent. But in fact, in reality, the sources may be correlated. So how to address this challenge in truth discovery? Another one is this spatial temporal data. So in many real applications, so the data are spatially and temporally correlated. So how can we address such, how can we find truth on such data? And then the third challenge is this long tail phenomenon. So in many real-world applications, the data sets have some such long tail phenomena. So that means we can see that many sources only give claims on a few objects. And then only a few sources make claims on many objects. So this is called this long tail phenomenon. So on this long tail data set, there are also some challenges when we conduct this truth discovery. And the last one is this fine-grained user expertise. So in previous truth discovery methods, we assume that each source has one source rate of self-reliability degree. But actually, the users may have different expertise levels on different topics. So let's talk about this work one by one. So let's first look at this source dependency work. Actually, many truth discovery methods consider these independent sources. So they assume sources provide information independently, and source correlation can be hard to model, but this assumption is often violated in real life. So, for example, there may be copy relationships between sources. So sources can copy information from one or other sources. And there may be other types of correlation. And there are these two major categories of methods that handle the source dependency. So one type of work assumes that the source correlation is known. So for example, in this social this method, so they assume that for claim, a source may copy from a related source with a certain probability, and this information is known. So then they use this maximum likelihood estimation method to estimate the claim being correct. And during this process, this known information, this known relationship information is incorporated. And another type of work considers unknown relationships. So the first one considers copy relationship. So we will talk about in a little bit detail later. And then the second paper, this W13 paper, models this true discovery problem as a probabilistic graphical model. And then during this process, related sources are grouped together and assigned with a group weight. So instead of modeling independent individual sources, they group the similar sources or correlated sources together. So let's look at this copy relationship problem in a little bit detail. So this work was done by Luna Dong. So she was with AT&T and Google before, and now she moved to Amazon. So these were basically the high-level situations for this copying detection is as follows. So basically, we can first look at the figure here. So the one in the middle represents these common objects between two sources. And the left one means the objects, indicates objects covered by source 1 only, but not by source 2. And then the right one indicates objects covered by source 2 only, but not by source 1. So basically, we first look at those common objects part. So if we find many same errors in this part, then it implies that the source 1 and 2 are related. And now we want to find out which one copies from which. Then we look at this source reliability inconsistency. So if we find that for within this source 1, this objects covered by source 1 only and this common objects part, and we find that they have similar accuracy degree. But when we look at source 2, we find that the common objects part and this source 2 objects part only have different accuracy degrees. Then we will say that this source 2 may be a copier. So source 2 copies from source 1. And then they incorporate this high-level intuition into this truth discovery process. So during this truth discovery process, we typically use a two-step iterative procedure. So we find out the truth, and then we update this source accuracy. And then in their method, they incorporate this copying detection component. So they first do this copy detection, and then find out the truth, and then derive this source accuracy. So at this copy detection step, so basically, you have already conducted this truth discovery and source accuracy computation. So therefore, the previous two steps, you can basically derive this copy detection based on these two intuitions. And then after they conduct this copy detection, they can go back to do this truth discovery and source accuracy computation. And then they conduct these three steps iteratively to derive the final results. And in another paper, this Sigma 14 paper,
So they consider more general type of correlations. So for example, like negative correlations. So the sources may provide data from complementary domains or may focus on different types of information. So they have negative correlations. Or positive correlations when sources may apply common rules in extraction. And then they conduct this hypothesis test of independence using joint precision and joint recall. So then the next one we will talk about is this real-time truth discovery. So this is a work my other student Yaliang Li has done, and we published this paper in last year's KDD. So the problem setting is as follows. So suppose we have multiple websites. They provide information about this stock price, but they have conflicting information, and we want to find out the truth. But as we know, the stock price is constantly changing. So therefore, the truth itself is evolving. So then how can we conduct this real-time truth discovery? So the major challenge is that first is efficiency. So when data comes sequentially, we don't want to do this batch version of truth discovery each time. So we want to do this incrementally. And also there are these temporal relations among entities, and also the source reliability may change. So some source may be reliable before, but may not be reliable now. So in this paper, we address all these challenges, but here we will focus on this incremental part. So we basically define the problem using this optimization function. So this loss function is actually similar to the CRH work we introduced before. So we have this, we basically measure the difference between each source observation, each source claim, and the true value, so which is indicated by this star. And WS indicates the source reliability degree. And then the last term is basically a constraint on this, the source weight. So we cannot make this source weight, unconstrained. So then we have established equivalence between this optimization problem and the maximization of error likelihood. So we ignored I ignored the detail here, but by establishing this equivalence, then we can derive an incremental version of this truth discovery algorithm. So it can dynamically update source weights and compute truth upon the arrival of the new data. So basically here, when each new data trunk arrives, we first update this source reliability. So this source reliability is encoded in this probability of this WS given this error observed so far. So we can see that, suppose the current time is T, and then we can see that this probability of WS given the error observed until time T can be updated based on this probability, probability of WS based on the error observed till T minus 1. So we just update this probability by the error observed at the time T. So after we update this source reliability, then we can use this source reliability to compute the truth. So this is incremental. This is basically an incremental truth discovery method. So then the next topic we will discuss is this spatial temporal correlations. So in many real-world applications, we have this spatial temporal data like traffic conditions, weather conditions, or gas price. So then on such data, how can we do this truth discovery? So this part, we did this truth discovery in the mobile sensing scenario. So the basic idea is that now each user can be regarded, or each human each person can be regarded as a human sensor. So because we carry some mobile devices each day, and we go along, for example, we walk around, and then our sensors basically can tell the real environment. So for example, suppose we are interested in this PM 2.5 value of a certain location, and there are different users who carry these portable devices who can give sensor values about this PM 2.5 value. But because of the variance in the sensor quality and the way people carry sensors, so they may give different values for this, the same location. So now we can conduct this true discovery to find out the true value of this PM 2.5 value at this location. But the challenge here is that the coverage rate of each user may be low. So that means each user, it's impossible for a user to cover all the regions in a certain city, right? For example, in San Francisco, you cannot expect one person traveling all the areas in San Francisco. And then for some unpopular area, it's very likely that there are only very few people who have sensor values for that area. So in this toy example, suppose this E8 is only observed by one user. That means there will be insufficient information for us to find out the true value. But because we have this spatial temporal setting, so that means the entities that are nearby spatially or temporally may have similar values. So therefore, we can use this correlation information to help us improve this estimation accuracy. So actually, we can borrow information from the nearby entities or correlated entities to find out the true value for this E8. So that's what we did in this Census 2015 paper by my student Trish Meng. So Census is actually a sensor network conference. So the input is actually the observations for N entities by K sensors. So here each sensor is regarded as a source. And then besides this information, we also have this correlation information among entities. And then the output will be the truth of each entity and also the reliability of each sensor indicated by this WK. And the truth is indicated by this XI star. So then we use this optimization function to solve this problem. So WK indicates this sensor weight, basically the reliability degree of the information provided by the sensor. And this is the true value of entity. And XIK is the observation. And then this SII prime is the similarity between the correlated entities. And the last term, actually, the regularization with this correlation information. So the basic idea is that, so this one is a constraint function on this WK. So actually, the first term was used in our CRH paper on this basic true discovery setting. So here we add the second term to regularize the values on correlated entities. So the basic idea is that if two entities are similar, then their true values should be similar. And then basically we have these two sets of variables, this X star, which is the true value, and WK is the source weight. So in our CRH work, we basically iteratively update this WK and XI star. But here, because we add this correlation function, so that means the entities are not independent anymore. So there are correlations between them. So therefore, we cannot independently update each entity's truth. So therefore, we basically modify this optimization function. So we partition the entities into disjoint independent sets. Then within each set, there are no correlations within the same set. So here I didn't talk about the details, but we developed several approaches to do this partition. So then after we partition them into this disjoint independent sets, now we can update the truth of each entity within each independent set. And then we can conduct this iteratively. So that's the basic idea. So here we show some experiments on this of this method on an interesting application, which is this air quality sensing. So it's basically the same setting I introduced in that toy example. So we want to monitor this PM 2.5 value. And then we have participants equipped with this device called mini AQM. So actually, these experiments were conducted by a collaboration with a startup company in Beijing. So you may know that people in Beijing care about this air quality. And there is a startup company which is developing this portable device to sense this air quality. But the problem with the portable device is not that accurate. And they have a more accurate version, which is called this thermal. But this thermal device is big, cannot be carried by person around. So this experiment, we want to show that by aggregating people's users' sensory input from this portable device, we can basically simulate the accurate value output by this thermal. So here is a figure showing these devices. So actually, the mini AQM value can be transferred to this smartphone app, and we can collect the value there. And we do a preliminary study. So we conduct this PM 2.5 sensing in these 4 areas in Tsinghua University. So here is our results. So we compare with several true discovery methods which do not consider this correlation information. So actually, the black curve is our method. So we vary this coverage rate of sources. So the smaller the value means that the coverage rate is low. So that means the user visits few places. And then the measure we use, the left-hand side is this mean absolute distance. And the right-hand side is this root square of this mean squared error. So we can see that our approach achieves better performance than the baselines, and especially when the coverage rate is low. So we can see that incorporating this correlation information can really help improve this accuracy, aggregation accuracy. So the next one I'll talk about is this long tail phenomenon on this south side. So we mentioned about this long tail phenomenon. So basically, in many data sets, we can see that only a few sources make many claims. And then majority of the sources only give claims to one or two objects. So then this gives a challenge when we do this truth discovery, because the essence of truth discovery is to estimate this source width or source reliability. However, if a source only give claims, for example, only give like 1 or 2 claims, then the source width cannot be estimated properly. So especially when there is this long tail phenomenon, then most sources give very few claims. Then most source widths are not properly estimated. So therefore, we propose a confidence-aware approach. So we not only estimate source reliability, but also consider the confidence interval of the estimation. So this work was done by student Qi. So this was published in last year's VLDB conference. So the basic idea is as follows. So we assume that the source is making independent errors, and it follows this Gaussian distribution with 0 mean, and the variance is this sigma s squared. And then when we conduct this aggregation, then we assume that we use this weighted combination. We assume that the error is also a weighted combination. Then this error follows also a Gaussian distribution with zero mean, and the variance is of this form. And then we give a constraint on the source weight. And then our goal is actually to minimize this variance of the aggregated error. And then this reduces to this optimization problem. So basically, we want to minimize this, the sum of this WS squared times this sigma S squared. But the problem is that this sigma S squared is not known. So we do not know the variance of each source error. Sorry. So one way to solve this is we can use the empirical variance. But the problem is that this sample variance is not accurate when we have small number of samples. So for those sources that make only a few claims, then this sample variance is not a good choice. So then we consider this confidence interval solution. So basically, we derive this statistics that on this left-hand side, which involves the sample variance and also the true variance. And this NS is the number of claims of each source. And found that it follows this chi-square distribution. And then based on this knowledge, basically, we can consider the possibly worst scenario of this sigma S squared as a candidate for this sigma square S. So basically, we use the upper bound of the 95% confidence interval of this sigma S squared. So we call it US squared, so which can be derived in this way. So the basic idea is that so we have a confidence interval estimation of this sigma S squared. And then we use that upper bound to represent this sigma S squared in our optimization problem. So here we plug in this US squared as an estimate of this sigma S squared. And then we can derive this source weight, which is the inverse of this US squared. So now I will use a twice example to illustrate why we use this US squared. So what's the benefit of using this US squared instead of this sample variance? So here we can see a toy example with 4 sources making different claims. So we can see that source A and C are good sources. So their sample variance is smaller, it's 0.1. And B and D are bad sources whose sample variance are 3. And then A and B are big sources, so they make 200 claims. And C and D are small sources, so they only make 2 claims. So first, we can see that although their empirical variance of the error are the same, so among this A and C and B and D, so we can see that the confidence interval are different. So for A and B, the confidence interval is more compact. So it centers around this the sample variance. But for C and D, the confidence interval is much wider. Is wider. So then when we calculate this source weight, we can see that if we just use the sample variance to estimate the source weight, then A and C will get the same source weight, and B and D also get the same source weight. So, but this does not make sense because source A gave 200 claims, but source C only make 2 claims. So our confidence in the estimation are different. So for source A, our estimation of the source weight is actually much more confident than source C. So therefore, using this the upper bound, this US squared, so we actually can greatly increase the source weights of those sources which give more claims. So here, comparing A and C, we can see that A have a much higher source weight because A make 200 claims. So therefore, this estimation that it's a good source is much more confident than the estimation of this source C. So therefore, we increase the weights of source A. And then for B and D, similarly, we increase the source weight of B because it's the estimation on this source is much more confident. So using this approach, then we have some good results. So here is a data set we use. So I didn't list the detail here, but later when we talk about application, we'll introduce this data set in more detail. So this actually was a data set. It's a crowdsourced question answering data set. So the basic setting is that there are smartphone users who participate in the game, this Who Wants to Be a Millionaire game. During the TV show, so these smartphone users will receive these questions and they submit their answers. So we aggregate these users' answers and try to recover the true answer for each question. And there are 10 different question levels. So 10 means the most difficult questions, and 1 means the easiest question. So this data set actually was collected from a colleague. And at that time, they just used majority voting to find out the true answer. But they found that for easy question, this solution works pretty well. But for difficult question, we can see that the error rate of majority voting is very high. It's over 50%. And then this colleague talked to me and said, can you improve the performance of this aggregation of these different users' answers? And then by using our approach, we can see that for the most difficult question, we basically can improve the accuracy to like around 80%. So by estimating this source weights accurately, we can basically greatly improve this truth discovery performance on this crowdsourcing question answering data set. So the next topic I will talk about is this fine-grained truth discovery method. So this was done by my PhD student, Fenglong Ma. So this was a paper appeared in last year's KDD. So in previous work, typically we assume a single user expertise. But we know that this may be violated in many applications because a user may be good at one aspect, but may not be good on another aspect. So in this work, we try to derive so-called fine-grained user expertise. And then we derive truths based on such fine-grained user expertise. So here, the fine-grained user expertise is defined based on topics. So we assume that a user may have different expertise levels on different topics. And then this topic is learned from this question and answer text. So in this work, we focus on this question-answer scenario. So here is the input and output of this problem. So the input is this question set. So in this toy example, is Q1 to Q6. And also the user set. So here we have 3 users. And answer set. So suppose each question have 2 choices. So user give different answers to a question. And also we assume we have the text of each question. And the text is represented using this bag of words representation. So the output first is these topics. So in this toy example, we suppose there are 2 topics. So this Q1 to Q3 belong to topic 1, and Q4 to Q6 belong to topic 2. And we have this, we want to find out this topic level user expertise. So we can see that a user may have different expertise level on different topics. And finally, we want to find out the true answer for each question. So we want to point out this Q3, this question Q3. So we can see that on this question, because this question belongs to this topic 1, and we can see that user 1 has the highest expertise level on this topic. So therefore, for Q3, we will use this user 1's, rely more on this user 1's answer to find out the true answer of this question. So here we didn't show the previous one. We can see that actually user one's overall expertise is not that high. So if we use user one's overall expertise level, then we cannot find out the true answer for this question. To solve this problem, we propose a probabilistic model to model this problem. So the basic idea is that we jointly model the question content and the user's answers by introducing latent topics. So the principle is that modeling this question content can help estimate reasonable user reliability. And in turn, modeling answers leads to the discovery of meaningful topics. So using this model, we can learn the topics, topic level user expertise, and the truth simultaneously. So in this model, we can see that the two parts share this ZQ, the generation of this ZQ. So ZQ is actually the topic indicator of this question Q. And then the left-hand side is actually we try to model the question text. So this part, we use existing approach, which is actually a variation of this well-known LDA model. So it's called Twitter LDA. This fits the modeling of short text. So because in this question answering scenario, typically the text is not long, so we use this Twitter LDA model. And then we will, I will mainly introduce the right-hand side, which is how to model the crowd's answers based on this ZQ. So this is the process of generating users' answers. So we assume that the correctness of a user's answer may be affected by the question's topic, user's expertise on this topic, and the question's bias. So the question's bias is actually can be regarded as a question's difficulty level. So if the bias is small, that means the question is easy. If the bias is large, that means the question is difficult. So the generative process is as follows. So we draw this, first draw this user's expertise level. Then we draw the truth from this uniform distribution. And then we draw the bias from this Gaussian distribution. Then we draw this user's answers using this logistic function. So the basic idea here is that we use this EZQU indicate this user's expertise, this user use expertise level on this ZQ, topic ZQ. And if this expertise and this BQ indicate the bias of this question Q. So if this user's expertise level is high and this bias is low, so if user's expertise is high, bias is low, which means the question is easy, so then it's more likely that the user's answer is the same as the true answer. So this AQU is actually the answer given by this user U on this question Q. And TQ is actually the true answer. And similarly, if the user's expertise level is low and BQ is high, then this probability is low. So that's the basic idea. So then we solve this problem. So we derive this solution by inferring the parameters and these hidden topics, hidden truths, and this expertise level from this probabilistic model. So here we show these results still on this data set. So we can see that by incorporating this topic level expertise, we can further improve this performance of this aggregation. So we can see that now for the most difficult question level, our accuracy can be improved further to around 90% accuracy. So this table basically shows the error rate. So the lower the better, but we can convert it to this accuracy. So for this, in this paper, we actually also show another interesting application, which is related to this knowledge-based construction. So we do a slot filling task. So the slot filling means that for a given question, like we want to find out the birthplace of a certain celebrity, and then we have a test corpus to extract such information. We may have multiple information extractors. We may have multiple different types of test corpus. And then we may have different answers for such questions. And then we aggregate these questions, the answers from these different sources to recover the true answer to these questions. And we also observed improved performance of this information extraction. I think I now have a little bit more time here. The next topic we will then cover is this active crowdsourcing scenarios. So in this scenario, basically, we will talk about some techniques that can, as I mentioned, in passive crowdsourcing scenarios, we have already just have the data collected and given to us to find out the true values there. But in active crowdsourcing scenarios, we actually can design some mechanisms to actively grab the information from the users. So then the question will be, how can we actively involve the crowd into this process to get better data quality in the raw data? And if we have better quality of the raw data, then chances are we can get better quality data integration results. So that's this active crowdsourcing scenario. Later, Qi will introduce some strategies to do this active, to encourage this active crowdsourcing, such as how to protect users' privacy during this process so that users can be so they don't worry about the privacy issue, so they can be more actively involved in this process. And strategies such as incentives mechanisms. So we give the users some rewards so that they can be more actively involved in this process. Or how to define good strategies to allocate limited budget. So there are still many interesting topics we will discuss. So those I think we can leave after the coffee break. So we can maybe first have the coffee break, and we can come back because it's a new topic, I don't want to start it right now. So after topic break, please come back and we'll talk more interesting results. Thank you.